Welcome back. So, this is lecture 35 in this course on Bayesian modeling. The topic of this lecture is MCMC sampling for data set with multiple observations. Okay. So far we have done MCMC sampling, we have done a couple of examples, but in those cases we had only 5 observations or so, right. So, those were more for the purpose of example. Those are not like real data set. In reality, when you collect experimental data, you would have a lot of observations. So, let us say that can go from 500 to thousands of observations, right. So, we will have thousands of observations from a single experiment, right. In that situation, it becomes slightly tricky, okay, to implement MCMC algorithm, okay. And let me show you how, why, okay. So, we are taking an example, so which I briefly discussed in the previous lecture. We are taking an example of reaction time experiment. So, you can think of any reaction time experiment. So, let us say you have 500 observations from a reaction time experiment. So, it could be, for example, a Simon task or a Stroop task, or let us say a word recognition task, right. Or let us say a very simple task where the subject is just pressing the keyboard key, let us say spacebar key repeatedly, and we are recording key press times, right. So, the typical distribution of such a reaction time data points is like this. It is a asymmetric distribution. We hardly see observations below 50, 100 millisecond. We see a median around 300 milliseconds, and then a long tail. So, some participants could be as slow as, let us say, 1000 to 2000 milliseconds, right. So, that is a typical data we see. So, let us say this is the actual data that you observed. So, OBS indicate actual data observed in an experiment which contained 500 observations. So, let us assume that. Okay. Now, we are interested in modeling these observations, these reaction time observations. So, we define our model first. We define the likelihood assumption that reaction time in ith trial comes from a log normal distribution with parameters mu and sigma, because that this distribution would be more reasonable to assume compared to a normal distribution, because it's asymmetric and it is never going to be less than 0. It would have longer tails on the right hand side. So, that is the properties of log normal distribution. And then we need priors on mu and sigma. So, for simplicity, let us assume sigma is fixed at 0.3. On mu, we have prior, this prior normal 6, 0.5. You can actually do prior predictive check to ensure that you are choosing a reasonable prior. Okay. From my experience, this is a reasonable prior when you assume a log normal likelihood for reaction time data. All right. So, our goal is to calculate the posterior distribution of mu given the data. So, let us implement MCMC algorithm. So, I will just copy paste the MCMC function, okay, and we will try to use it directly here. All right. So, now we are all set. So, this is my MCMC function. I will still define number of samples, step size, all these things will remain there. Then I created an empty Markov chain. I initialized the Markov chain. Now I can draw from a different distribution because I'm drawing these samples for mu. So, let us draw samples from prior distribution of mu. Let's say R norm 6, 0.5. Okay. And then this will become current state of the chain. Now, for proposal generation, I can do the same, but would there be lower bound and upper bound? Yeah, you can define a lower bound of 0. Mean can be, because this is about average reaction time. So, we do not want it to be less than 0. So, it is fine, I think. So, you can do this, but this is not a constraint actually on the model itself. So, if you want, you can remove this. Okay. So, that wouldn't change anything. So, if you just do this, it is fine. Now, here you would calculate the likelihood of the proposal. So your likelihood distribution is actually log normal. So you will use DL norm. Okay. So the likelihood function is log normal. So observation rather than lambda mu, basically the mean is proposal theta, and then you have directly sigma. So what is sigma? 0.3. I think we should write it here. Sigma is fixed at 0.3. Okay. So you can just directly use sigma here. Okay. Now for prior density, prior distribution is normal. So proposal theta, mean of this density was 6, standard deviation 0.5. Likelihood for the current sample would be product of, rather than d poise, DL norm, because you have log normal likelihood rather than lambda. So this current state is the mean mu parameter, and the sigma parameter is sigma. Okay. And here rather than d gamma, again d norm. So current state, mean 6, ST 0.5. And then forward transition, backward transition will remain the same. You calculate Hastings ratio, probability of acceptance, the rest everything will remain the same. Okay. So now I try to run this. Okay, step size of 0.5. I think it's fine. You can actually make it a smaller. So let's say, I think 0.5 is fine for now. Let's make it 0.1. Okay. So what happens is this, that it throws you an error. So there is error, it seems, in generating the proposal. So unused argument. Oh, sorry. So this will happen. So I think because this is parameters usually mean. Okay. Fine. Okay. So let us try it. So you see this error. So there is error in this statement if accept is equals to 1, missing value where true false needed, right? So there is something wrong. So basically your accept is not 0 and 1. So that means problem is coming in from calculating probability of acceptance. You are not able to do that, and that means you are not able to calculate Hastings ratio properly. Okay. So let us begin step by step. So where this problem is occurring. Okay. So what I will do, I will start with I equals to 1. Okay. So from here I equals to 1. Let us sample current state of the chain. Sorry, let me create empty theta chain. I equals to 1. So okay, number of samples not found. So let me just say number of samples is 5,000. Okay. So now, so created empty theta chain, and now I created current state of the chain. So this is my current state of the chain, 5.36. Okay. So I store it as current chain. So this should be 5.36. Now I generate a new proposal for parameter mu, and it is new proposal is 5.28. So everything is fine so far. Okay. Now let us calculate likelihood, prior and forward transition, backward transition for all this, and let us calculate H. So let's see what is H. H turns out to be NaN. Why? Why this is happening? Let us see what are the, if prior density is calculated correctly. Yes, so prior you were able to calculate 0.28, backward transition 2.79, forward transition 2.79. They will be equal because it's normal proposal density. Prior current is 0.35, likelihood current is 0, likelihood proposal is 0. Basically what you're trying to do is 0 divided by 0. That's why it is giving NaN. Why both the likelihoods are 0? Because what you are doing when you are calculating the likelihood, you are calculating a likelihood value for each data point. Okay, see, you are calculating a likelihood value for each data point, but you end up getting 500 such likelihood values because you have 500 data points. When you take their product, it comes out to be 0 because R would have these computational limitations. So if it goes beyond a certain number, it would give you 0. Okay, so it goes below a certain number, it will give you 0. So this is happening um, because of computational threshold of R. So how low number it can give you. If it cannot go lower than that, it will give you 0. Okay, so that's the problem. Okay, so that's why this sampler wouldn't work if you would have a lot of data points. Let's say even more than 50 data points, it wouldn't work. Okay, so how do we solve this problem? Okay, so we need to solve this problem. So let us see. So what we are trying to do is this when we are calculating joint likelihood. So let's say you have some proposal theta star or any current state theta I, whatever, your proposal theta star, and your data points x1, x2, x3 up to xn. So these are data points and this is let's say a proposal. Okay. My goal is to calculate joint likelihood of theta star given all these observations. So what is the likelihood of joint occurrence of all these data points x1 to xn when parameter values theta star? Okay. So what is the likelihood that this parameter theta star would generate jointly all these observations? So that's your joint likelihood. Okay. So we want to calculate joint likelihood of theta star. So it's given by this. How do we calculate this? This is something we know from when events are independent. So assuming all these data points are independent, what we can do, we can calculate likelihood of individual data points and multiply them. So this is something we can do when these events are independent. So we calculate this using this approach. So we calculate likelihood for x1, we multiply it with likelihood for x2, likelihood for x3, and so on. So we take product of all these likelihoods. So basically we write it like this, product of likelihoods from 1 to n. Okay. So this will give you joint likelihood. But the problem is that although you can calculate likelihood of individual data points, but when you take their product, it gives you 0 because of computational limitation of R. So how do we do? What do we do with this, right? The point is that you are actually interested in the ratio of likelihood, joint likelihood into prior density of theta star and joint likelihood and prior density of current state of the chain. So let us call the current state theta z. Okay. Likelihood and prior density of current state of the chain. So you are interested in this ratio. Okay. Can you calculate this ratio in the situation when you have a lot of data points? So if you directly go on multiplying these likelihoods, then this term will be 0 and this term will be 0. So you won't be able to do this. Okay. What if rather than, so this is ratio for, this is called Hastings ratio, right? So ratio of these things. You can also add forward backward transition kernel, but that's not a concern for us. So what if rather than calculating h, okay, what if I calculate log of h? I mean, if h can tell you something, whether you should accept or reject the proposal, log h can also tell you something, and you later can take its exponent as well, right? That's totally fine. So can I calculate log h? So what would be log of h? Log of h would be log of this thing, log of likelihood theta star, sorry, theta star given x1 to n, prior density of theta star divided by likelihood theta j x1 to n, prior density of theta j. Okay. So, do you remember this identity? So, if we try to take log of a divided by b, this becomes, this can be given by log a minus log b, of course with some constraints that, for example, a and b should be greater than 0 or so. So, this is an identity. So, if you calculate log of a divided by b, you can rewrite it as log of a minus log of b. So, here we are in same situation, we are trying to calculate log of likelihood into prior for proposal divided by likelihood into prior for the current state. So, that means we can rewrite this statement as log of likelihood of theta star minus log of likelihood of current state of the chain and prior density of current state of the chain. So, you can write it like this. Now, log of a into b will be log a plus log b. So, we can rewrite this statement like this. So, log of joint likelihood of theta star plus log of prior density of theta star minus log of joint likelihood of theta j minus log of prior density of theta j. Okay. So, this is what we get. Okay. So, this will give you basically log of h, and later on you can also take its exponent. But why does this help us? What does it solve? What does it solve is this. What is joint likelihood? You have the formula of joint likelihood here. Right. So, joint likelihood is product of all these individual likelihoods. Let us substitute that in this new formula. So, you can rewrite this like this. So, this is joint likelihood theta star. So, you can write it like this, product of likelihoods of individual data points, okay, then plus log of prior density of theta star minus, similarly here, log of product of joint likelihood of theta j's minus log of prior density of theta j. Okay. Now, let us expand this term and this term. So, what you are trying to do here, you are trying to take log of product of certain thing, right. So, log of a into b into c into d, right, and that can be written using identity of logs as log of likelihood of observing x1 plus log of, so basically you can take summation across all these, log of likelihood of observing x2 and so on. So, I have just expanded this term. Okay. So, basically you can rewrite this whole expression like this. So, the first thing would be summation of log of likelihood of individual data points from I is equals to 1 to n. So, basically this thing can be rewritten as this. So, log of product of likelihoods is equal to summation of log likelihoods of individual data points. Then you have log of prior density of theta star, then minus summation of log likelihood of theta j's minus log of prior density of theta j. Okay. So, now we have got this in form of log, and we do not need to do any product anymore. So, we do not need to multiply anything anymore. What we are doing here? We are summing log likelihoods. And how does it solve our problem? Because log likelihood for a particular individual data point would be some negative value. So, let us say somewhere around minus 300 or so. or maybe minus 3000 or so, and you are just adding these numbers. So, minus 3000, minus 3500 and so on and so on, right. So, what this will end up giving you will be a large negative number, but it won't be in the range of, let us say, 10 to the power 500 or so. It would still be in reasonable range. So, this would end up giving you large negative number. This will also give you a large negative number, okay, and we are basically subtracting this large negative number from this one. So, anyway the difference would be a small negative number or a small positive number, whatever, right. So, that way in the end the value log h would be some reasonable number, okay. So, we are not never going to have problem in calculating log of h, right. And once you have calculated log of h, you can take exponent of log h to calculate your criteria, okay, or you can decide some other criteria as well, okay. So, that is basically, for that you can take some choice, and different algorithms do take different choices, right. So, you can take exponent of log h and decide based on this, right. You can also calculate something called transition probability. So, let us say I decide that I would transition from state theta j to theta star, okay, with some probability p, and this probability p, transition probability, would be given by exponent of basically minus log posterior density of theta star minus log posterior density of theta j or something like that, right, which is basically log h, right. So, exponent of minus log h, you can also divide it by k or something. Okay. So, this is the idea. So, what we are going to do, we are going to operate on log scale now. So, we will calculate, rather than calculating Hastings ratio, we will calculate log of Hastings ratio. So, basically we will calculate log likelihood, log prior density, and we will take their difference to calculate log h. So, if let us say this if log h is, let us say, 0, then basically both proposal and the current state are at same posterior density, exactly same posterior density. If log h is negative, that would mean um, that the current state is in higher posterior density region. If log h would be positive, that would mean the proposal is in higher posterior density region. So, that means if log h is positive, you would always accept the proposal, okay. So, let us implement this in R. So, what the change that we need to make here now is this. So, rather than calculating product of likelihoods, we will calculate, because we are going to calculate log likelihood of the proposal. So, let me also write it that way. So, log likelihood of the proposal would be summation of these likelihoods, but it should be on log scale. Okay. So, when I put this argument log equals to true, this would give me these likelihoods on log scale. See, minus 6, minus 11, these are small negative values, and when you take their summation, the log likelihood would still be a reasonably small negative value. So, minus 3451, right. Similarly, here as well, I will also calculate, now I will calculate everything on log scale. So, log equals to true. So, this is log prior density of the proposal. This is log likelihood of the current state. So, rather than product, I will take summation of all these things being on log scale. Here as well, it would be on log scale, right. Okay. So, now I have everything on log scale, and rather than taking product of likelihoods, I am taking summation of log likelihoods. Similarly, for backward transition and forward transition. So now I've gotten these things, right? Now rather than calculating h, I will calculate log h. So which would be log likelihood proposal plus log prior proposal plus log backward density kernel, and then rather than divide it would be minus log likelihood current, log prior current, and log forward. Okay, so I have gotten now log h. So now for this, so now from log h I can calculate h. So h is, let's say, exponent of log h. Okay, and now I can keep on doing the same things, okay, in the later part. So this will give me log h of minus 174, and when I calculate h from this, the h comes out to be 1.44 into e to the power minus 76, right. From this I can calculate probability of acceptance, which is in this case this, okay, and now I can decide my acceptance and rejection criteria. Okay, okay. So this is how I'm basically now dealing with this problem. I calculated everything on log scale and operating on log scale now. I calculated log h, which I transformed into h, and I calculated probability of acceptance from this. Okay. So let us try this. Okay. So this is my algorithm, number of iterations, step size of 0.1, and let us sample for these 4 chains. Now I shouldn't see an error, although it is the sampling is slow. That means perhaps your step size is too large, so we can decrease it in further iteration. We can check the rejection rate. Let us check the rejection rate. So rejection rate is 83. I think so it is too high. So maybe 0.05. I think it would be still 70-80% or so. Yeah, around 70. So you can go even with lesser step size. 0.01 is reasonable. You can go even lower. Okay, this is good. So it gives you 23% rejection rate. So this is good. So let us first visualize our chains. Sorry, I made a mistake. So this is how chains look like. So chains are mixing well, and they are sampling from the actual posterior density, which is somewhere around 5 point, I don't know, 5.6 or something, okay, 5.7 or something. So this is good. All the chains started at different places. So some of the chains started here, some chains started here, but they are still converged very quickly. You can also visualize the posterior distribution. You can calculate at least the quantile of the posterior distribution. So let me calculate the quantile of df post samples. So I'm going to calculate 95% credible interval, so which comes out to be 5.67 to 5.72. So 5.67 to 5.72, okay, which is good. I think the actual true parameter value that we took to do this was 5.7 or so. So this is really good. Okay. So you can also visualize the histogram of our posterior distribution. This is how the histogram looks like. Yeah, so the basically this central tendency is around 5.7 or so. Okay, you can see the mean, but that's actually not very important statistic in Bayesian framework. So I would suggest that don't get interested in mean of these posterior samples, because that does not tell you anything. What is important is, of course, this 95% credible interval, but because this gives you information that you can say with 95% certainty that the true value lies between this and this range. Mean does not tell you anything, because we are always interested in uncertainty. So there is some true parameter value and there is some uncertainty about it. So we are estimating the distribution. So we are interested in whole distribution, not some mean or average tendency of the estimates, right? Okay. So one thing we can do now is compare this with a posterior distribution estimated using grid approximation or importance sampling. So let us try this with grid approximation. So let me draw a lot of values of mu from, let's say, a uniform density. How many? Let's say 4 lakh. Okay. And between what and what? Let's say between 5 and 6.5. Okay, so 4 lakh values of mu between 5 and 6.5. Now for each value of mu, I'm going to calculate the likelihood. Okay. By the way, here again, it would be impossible to calculate the joint likelihood because it will always give you 0. So rather than calculating joint likelihood, you can calculate log likelihood. So basically apply the same approach. So what would be log likelihood? So let me write it like this: repeat NA 4 lakh times. So I will calculate log likelihood for each sample. So I will run a loop for I in 1 to 4 lakh. Okay, so we'll calculate log likelihood for each proposal I, okay, using this. So this is how we calculate a log likelihood. So basically it's summation of log likelihood of individual observations. So rather than proposal theta, all we need to give here is mu I. Sigma is fixed as 0.3, so I don't need to worry about this. So this will calculate log likelihood for each value. If you want to visualize how it looks like, you can plot mu versus log likelihood. Okay, it is taking some time. This is how the distribution looks like, log likelihood looks like. I think we should have taken more values because it seems cut off at 5. Okay, so maybe I was too conservative here. So let me take it from 4 to 7, or maybe 3 to 7. It will take a little bit of time because there are a lot of samples. Okay, and now you can already visualize the problem. Said that in order to get, let's say, 40,000 samples from the posterior, you will need to have at least 4 lakh grid points, right? So you want at least 10 times more or so, right? So it is already becoming difficult when you have a single parameter. So what would happen with 2 parameters? It's going to become very difficult. Okay, so there is a problem, it seems, again at 7. I'm not sure what is happening here. Let us just ensure that okay are uniform. Okay, this is reasonable, so you can even go more. I think also if I turn this into expectation of this, so maybe I will have slightly different graph, because I was just drawing the graph of log likelihood, so that is supposed to look like this. I think it's not able to compute it, so everything is turning out to be 0. Okay, fine, so we'll just go with log likelihood. Okay, now this is fine, we have calculated log likelihood. Now we also need log prior for each proposal. So how do we do that? So we use d norm because that was our prior. We will calculate it for each parameter mu with the mean 6, standard deviation 0.5, log equals to true. Okay, so get log prior corresponding to each parameter, each sample. Now log posterior would be log likelihood plus log prior. Okay, so this would be log posterior, basically log of unnormalized posterior. So we have gotten now log posterior. Now let us sample based on log posterior as weights. Okay, so to get post samples with grid approximation approach, we will sample from mu. How many samples? Let's say 40,000, and probability being, let's say, log posterior. Actually, it doesn't matter whether this vector contains actual probabilities or not, or whether the summation is equal to 1 or not, it will still work. So as because it considers them as weights. I am also, although not sure whether negatives will work, so maybe we'll have to turn them into positive or something. But let's see. Replace equals to true. Okay, so negative probabilities don't work. So what we can do is something like this. So basically you have normalized these log posterior densities, right? So this may work now. So now we have got samples from the posterior using grid approximation. Let's see how do they look like. Ah, they look really weird. Okay. So I don't know, I just wanted to use them as weights. So let's see if any of this approach works. Okay, so this slightly works, but I don't think this is giving us actual posterior. I think we need to uh, make some sort of like, we need to figure out a way how to assign weights to each posterior based on log posterior densities. Okay. So one way could be to, let's say, um, subtract something from those, let's say log posterior minus sum of log posterior or something. So basically here what I'm doing is I'm scaling them like this, and what would this do? No, it doesn't work. So they are on a particular scale, right? So what if I divide them by 50,000? Okay, and now take exponent of all these. So let me just draw histogram of these weights. Okay, so this seems to be working fine. Okay, so now I'll use these weights as probability. Okay, so this is much more believable. So this is much better. Yes. So now you are getting consistently same shape. It's just that the slightly uh, the proportion by which you are dividing, that is changing slightly, because getting the range between 5.4 and 6.0 or so. Okay, so seems to be working fine. Okay, so now you can try to compare. I think it would look very different from the posterior that you collected using MCMC. Okay. So method is grid approximation. Yes, it seems to look quite different. What we can do instead, rather than having color method, we can do facet trap as well. Okay, so this looks quite off in the sense that we are getting a very wide posterior here, but that could be due to the constant that we use to divide the log posterior density, right? So you can figure out a better way to deal with this. Yeah. But overall, the Markov chain Monte Carlo would have a good posterior recovery compared to grid approximation, as especially when we go into from one parameter model to two parameter or more, right? and it also will converge faster. So it has much better efficiency. Okay. So anyway, so this concludes our lectures on Markov chain Monte Carlo. So in the next couple of lectures, I will cover one more sampling algorithm, that is Hamiltonian Monte Carlo. I wouldn't go into too much detail of Hamiltonian Monte Carlo. We just need a basic introduction and how it works, and maybe one sampler example, just to get a hang of it, because the packages that we will be using in R, they actually use Hamiltonian Monte Carlo sampler, and it is much more efficient than MCMC in terms of, for example, in terms of proposal generation, because it generates proposals in such a way that your rejection rate is quite low. So basically your algorithm is quite efficient for even for very complex models. Okay. So all right, I will stop here. In the next lecture we will do Hamiltonian Monte Carlo. All right, thank you.